Hey, how are you doing, guys? I'm Dohan. Here's lesson 3 part 2, which is about cross validation. So for today's video, first I'm going to explain to you what is cross validation through an example. Then I'm going to show you how to implement this in code by using scikit-learn library. And here's our outlines for today's video. First, we are going to define our example, why we use data, what is cross-validation, define our task, how cross-validation work, what is IndexSplitter, why we use random.shuffle, make our IndexSplitter. Then we are going to create our dataset, create our KFold object, build our training group, and finally ensemble it. So let's get started. Okay, so let's begin with an example. So here's some data and we want to use variables chest pain, good blood circulation, etc. to predict if someone has heart disease or not. So if a new patient shows up, we are going to measure these variables to predict if this patient has heart disease or not. First, we have to decide which machine learning method would be best. So this is a classification problem. We could use logistic regression, or k-nearest neighbors, or support vector machines, and many more machine learning methods. How do we decide which one to use? So cross-validation allows us to compare different machine learning methods and get sense of how well they will work in practice. So imagine this blue column represented all the data that we have collected about people with and without heart disease. So we need to do two things with this data. First, we need to estimate the parameters for machine learning method. In machine learning lingo, estimating the parameters called training the algorithm. Then we need to evaluate how well our machine learning methods work. In machine learning lingo, evaluating the methods called testing the algorithm. So we need data to train the machine learning method and test the machine learning method. A third approach would be to use all the data to estimate the parameters, which is known as training the algorithm, because then there wouldn't be any data left to test the method. So reusing the same data for both training and testing is a bad idea because we need to know how the method will work on data it wasn't trained on. The slightly better idea would be to use the first 75% of data for training and the last 25% for testing. And we could then compare methods by seeing how well each one categorized the test data. How do we know that using the first 75% of data for training and the last 25% of data for testing is the best way to divide up the data? What if we use the first 25% of data for testing? So for this, we are going to use cross-validation. So what cross-validation is going to do, it will use every block of data for testing and then summarize the results at the end. So for example, in the first loop, it will use the first block here for testing and other blocks for training. And in the second loop, it will use a second block for testing and other blocks for training, and so on until all blocks are used for testing. So cross-validation use all blocks of the data one at a time for testing and then summarize the results at the end. So in the end, every block of data is used for testing and we can compare methods by seeing how well they performed. So here's the results of logistic regression, support vector machines, and k-nearest neighbors. And as you can see, support vector machines is the best one. And notice in this example, we divided the data into 4 blocks, so this called four-fold cross-validation. And in extreme cases, we could call each individual patient as a block, so this called leave one out cross-validation. So what is KFold cross-validation? It's a popular technique, allows you to get most out of your data through ensampling. We can get better predictions because you can run many models on the same source data. Here is my notes, and let's begin with our task. So for this task, we are going to use ImageWolf dataset, and what we need for this task. So here we only need our training set and our test set. We don't need any sort of validation because we need to know how all of these models are performing. So this is where our test set comes in. Okay, so how does validation work? Let's review what we have covered in the previous example. So for this task, we are going to separate our data into 90% for training and 10% for testing. From there, we are going to take our 90%, which is for training, and generate n datasets by slowly shifting what the validation is. So no two models see the same validation data, but all graded on the same test data. So here we import basic version callback library, then we grab our dataset, and here we make our batch transforms and item transforms by applying some sort of data augmentation. And for our task today, we are going to use IndexSplitter. So IndexSplitter splits our data into training and validation sets based on list of indices. So it takes a list of indices and split a data into two parts, one containing the indices specified as validation set, and other part for training. And notice we use IndexSplitter because KFold accepts a bunch of indices to declare what our validation set is. Okay, so here we grab our train and test images, then we randomly shuffle our training set. So why we do this? So if by happenstance one class that's not in our training set happens to be in the validation set, then we're gonna throw a mismatch error. It's gonna say I was expecting 10 classes to pop out, but you give me only 9. By this way, we guarantee that everything shows up there. Then we print the len of our training images, which is 9025. And then we print our training images. So here is the path of our training images. Now we are going to make our IndexSplitter. For this, we need to define our starting and ending value for when we want to define our validation set. So for this task, we are going to take the first 80% of data for training, and the remainder part would be for our validation set. So here we define the starting part of our validation set by subtracting the length of our training set minus the length of training set times 0.2. And here we define our indices from starting to the ending of our training images. Then we pass this indices to our IndexSplitter. Then we pass our training images to our IndexSplitter, and here we turn our splits to a list, and then we add every index after our training images because that's how we expect our test images to be. So here we have 7,224 training, 1,805 for validation, 3,929 for testing. And here we create our dataset. So we pass it our training images along with our testing images, and the second parameter here specifies the transformations. Then we pass it our split list. Here we show a batch of our images, and then we are going to build our CNN learner by passing our data loaders, our ResNet34 architecture, and our accuracy metric. Then we are going to fit it with one cycle, and as you can see here, the accuracy is 8%, so we need to improve it by using cross-validation. So first of all, we need to grab our KFold from Sklearn.model selection. Then we need to declare how many splits we want. So here we declare that we need to split our data into 10 blocks, and we pass it to variable KF. Here we build our training loop. So first of all, we create our IndexSplitter with these validation indices. Then we split our training images and convert it to list. and add to it our test images. And here we create our dataset again, create our data loaders and call CNN learner fit with one cycle. And here we grab our validation percentage and add it to our val PCT list. Then we get our predictions of our test set and pass it to our test underscore predictions. And here's my notes. And as you can see, here's the accuracy. So the accuracy is improved. Now let's go through and ensample it. So ensampling involves averaging the raw predictions from our model and then take the solid mixture that has the best results. So first we need to make sure that B has the accuracy that we want. So we can double check this by grabbing the first list from our test predictions and pass it to our accuracy function. So if we go back to our first model, the accuracy is 23%, and here the accuracy is 26%. So we do a little bit better. Then we go through and make sure that this looks like the same for all of the predictions. Okay, so now let's go ahead and add all of them together. And if we divide all of these by the total number of predictions that we had, our accuracy is almost at 29%. So it increases around 6% from the worst case, which is the first model, the accuracy was 23. And it increases around 3% from the best case, which was 26%. So that's it for today's video. Hope you enjoyed.